Welcome to Streaming Data into Delta Lake with Rust and Kafka, or if you prefer, how Scribd reduced data ingestion costs by 95%. My name's Christian Williams. I've been a software engineer since 2006. I'm a contributor to Kafka Delta Ingest and Delta RS, which are two of the Rust projects that we'll be talking about today. I work for Scribd. Our mission is to change the way the world reads. We are the initial sponsors of the Delta RS and Kafka Delta Ingest projects. I've been at Scribd since 2019, and I can tell you it is a great place to work. So first, I'll go through the agenda for today's session. I'm going to start by giving some historical context leading up to the Rust implementations that we'll be discussing today. I'll just describe the problem we were trying to solve with Rust and go into some details about our Rust implementations. I'll mention the performance we've observed, the architecture and design, and what it looks like in our production deployment. Finally, I'll finish up by talking about the future of Kafka Delta Ingest and just sharing some general thoughts and experiences that we've had from Rust. And at the end, we'll do some Q&A. All right, so we're going to start with a bit of history. So before we did streaming at Scribd, we had self-managed Hadoop and Kafka clusters. Kafka wasn't the only platform we used for event logging. And even where we were using it, the Kafka topics we had a variety of unstructured data formats, some JSON, some CSV, and just some bespoke custom encodings. And we didn't have any streaming consumers. We had Kafka producers, a bunch of applications logging events into Kafka. But we didn't consume those in real time anywhere. Instead, what we had was in our nightly pipeline, we would read a day's worth of Kafka messages and load those into Hive partitions in our Hadoop cluster. So we wanted to do a few things. We wanted to standardize on Kafka for event logging. We wanted to standardize on JSON for our topic data format. And we wanted to convert those nightly tasks that loaded data into our Hive catalog into streaming jobs. We wanted to do that to take some pressure off of our nightly runtime and also to make event data queryable in real time. So the first step we took was to migrate to a managed Kafka. We chose AWS MSK, managed streaming for Kafka, for that. And we also, at the same time, we began adopting Databricks and Delta Lake. And some of the things we liked about Delta, we loved the optimize and vacuum commands because that makes it easy to clean up and compact small files. Streaming workloads have a tendency to produce a lot of small files. And we liked the fact that you can use Delta tables as streaming sources as well. So we could have streaming pipelines that start with Kafka and then continue on with Delta tables. So our first approach for writing events to Delta Lake was a generic Spark-structured streaming application. So we built this application that could be used generically using some config parameters. And it was a pretty simple Spark query like the one you see on the screen here to just read JSON from Kafka and write it to a Delta table. We used the Delta table schema to define the JSON deserialization format. And in general, the table schema for each event stream was the same as the JSON structure. But with a couple simple transformations to include a date partition and also add Kafka metadata fields so that we could keep track of each record, exactly what partition and offset and topic it came from when we queried our Delta table. So we had a lot of topics to write to Delta, and we had demand for a lot more. So our topic our topic volume was highly variable. So we had some very large topics and some very small topics. We didn't want to have a Databricks job per stream running this Spark application, so we lumped some streams together into coarser-grained Databricks jobs that would run many queries simultaneously, each one taking a particular topic into a particular table. Some downsides, and that's what you see here. So like on the Kafka side, you have like the purple cylinder, 3 of those. We have 2 topics going into that are being consumed from one Spark job, and within that one Spark job, we have 2 different streaming queries running, doing the work. So this was especially our strategy for small volume topics. For large topics, where a cluster using a dedicated Spark job didn't seem too wasteful, we would give it its own dedicated job. So some downsides of this approach, one was so our streaming queries weren't always isolated from each other. So if something went wrong in one, like the whole job fails, not just that one query. And we tried to group topics together logically, but this was a challenge because there wasn't a really great grouping mechanism that was kind of a good reason to put topics into the same job. So aside from this setup, we also created a nightly task for running optimize and vacuum on each of our streaming tables. After we implemented this, we quickly realized we wanted something better. Some of the other downsides was the cost was high for running all of these Spark jobs, 24 hours a day, 7 days a week. Some of our jobs would fail and restart occasionally, and there wasn't always a clear cause when looking through the logs. The operational plane for managing these jobs was a lot different than what we were used to for a lot of our other services. We typically have like a big Datadog dashboard with lots of metrics and logs, and with our streaming jobs, we didn't have that. At least not as many metrics as we're used to. Also, we couldn't effectively auto-scale. So we started wondering, could we append to Delta tables without Spark? Could we do it with a bunch of little headless Fargate containers that run like traditional services and aren't part of a Spark cluster? So this is where Delta RS comes in. So my former colleague, QP, I'm told he went Insanity Wolf and did a Rust spike, which implemented the Delta transaction protocol and a storage abstraction. And he called this Delta RS, and he created an open source repo for it. So at this point, we had a Rust implementation of the Delta protocol in hand, and then we were like, all right, well, now all we have to do is implement streaming rights. Sounds easy, right? It kind of does sound easy because, this is a very specific problem that we were trying to solve. We only needed to append records to these ingestion tables. We didn't need to do any filtering, joining, aggregating, or sorting. We basically didn't need anything that would require a Spark shuffle or coordination or detailed coordination between nodes in a cluster. We only needed this tiny subset of features. We only needed to append, and we decided we could use Kafka's consumer group feature for partition assignment so that we could avoid service-to-service communication between tasks handling the same stream. Also, we figured we could continue to rely on our nightly Delta optimize and vacuum to clean up in case we produced small files while we were streaming. So that's why it's easy. It is still kind of hard, though. First and foremost, we have to be very careful to not corrupt the Delta transaction log. We have hundreds of batch jobs downstream from our ingestion tables, and we don't want to break any of those downstream jobs because they're hard to fix and they take a long time to get running again. We knew we had at least a few topics that were large enough that they would require multiple writers. And we also had the problem that we use AWS and S3, and S3 doesn't support put if absent semantics, which makes it really hard to, well, it complicates at least the keeping the transaction log pristine and not corrupting it. I'm not going to talk a lot about the missing put if absent semantics. If you're not familiar with that concept, QP actually gave a great talk yesterday that goes in depth on how exactly how we solved for that in Delta RS. So the other thing is, we don't want a bunch of duplicates or lost data, so we got to be really careful with our Kafka offset tracking and rebalance handling. So we said, you know, given the easy parts and the hard parts, we still feel pretty confident we're going to do this in Rust. So just the basic setup is we have Delta RS providing the Delta transaction protocol and the storage abstraction. And within Delta RS, we use the S3 storage abstraction, which includes DynamoDB in order to enable atomic rename of transaction log files to kind of protect us from corrupting the transaction log. And on top of that, we added Kafka Delta Ingest to consume from Kafka, buffer messages, and write to Delta Lake periodically. So Kafka Delta Ingest it's basically an implementation of that same Spark streaming JSON query that I showed you earlier. A simplistic example of starting it up looks like this. You invoke Kafka Delta Ingest, you tell it to ingest from, in this example, my topic, and you tell it to write to a specific location, and in this case it's writing to a Delta table stored under my bucket, my database, my table. Oops. Here's a slightly more realistic example. There's tons of command line arguments for Kafka Delta Ingest to kind of tune the daemon to run according to the size and the size of the topic that you're handling and how often you want your writes flushed, and how large you'd like your files to be. Also, there's an argument mentioned here that lets Kafka Delta Ingest know to write transaction log checkpoints after every 10th commit. We also have some basic support for message transformations, and this is how we derive our partition column, as well as add Kafka metadata to the message before it's written to Delta. So let's talk about performance a little bit. So we don't have any official benchmarks, but we have plenty of prod examples because we're running somewhere between 70 and 90 of these Kafka Delta Ingest services in production right now. So I've selected 3 examples to kind of go over what kind of performance we're seeing for different workloads. None of these are giant, but we have a decent sized one in example 3. We have, like I said, a large variety of low volume topics and a few high volume topics. So example 1, we're running a single Fargate task with 1 vCPU This one's slightly over provisioned because it's using less than 40% of the CPU. It's handling about 3,000 messages a second. The average message size is about 2,000, or I'm sorry, 2K. Example 2, we have a single Fargate task running on a quarter vCPU, which is really cheap, handling about 1,000 messages per second. Message size is about 1.2K. Third example, this is one of our larger streams. We have 3 tasks. We're doing a 2 vCPU Fargate on that one. We get about 8,000 messages per second, but that one varies a little bit. We climb over 10 or 11 sometimes. The average message size on that is 3K. So that's kind of what the Kafka Delta Ingest deployments look like for those 3 examples. Here's a little bit of a cost comparison, comparing Kafka Delta Ingest to our prior Spark structured streaming approach, which I didn't mention this before, but we called that one Kafka Delta Streams. That was not open source, by the way. That was just an internal application. So rather than going over all the instance types, since we're already getting a little short on time here, I'm just going to mention the pricing differences that we realized. So we had, for example 1, that pipeline was costing us about $5,200 annually. With Kafka Delta Ingest, it's costing us about $400. Example 2, we went from $3,900 annually to $100. And in example 3, we went from about 23 grand annually to 2,200. So why is our Rust implementation so much more efficient? So first off, Spark is a big, massively powerful distributed processing engine with tons of features. And we don't need all that. So with a specific use case we're solving for here was append-only Delta workloads that are pretty simple. We got to read some data from Kafka and occasionally create a new file and update the transaction log. So next, Rust is way more efficient than Java. And also, finally, Fargate is cheap, and a quarter vCPU is actually plenty for a lot of our streams. All right. I'll go over the architecture and design a little bit here. All right. So the way to look at this diagram is, it's kind of an infrastructure diagram with numbered edges, so I can kind of talk through each edge and describe what's happening data flow wise. There's also an exploded view here, which I'll get to. So first, the big green number 1 circle. Producers send messages to Kafka. We have lots of different producers written in various languages. Step 2, we have our ECS tasks, read from Kafka. And here we have the exploded view, which shows, depending on the topic volume, we might have more than 1 task handling that topic. Or if it's a small topic, we might have a single task handling it. Our Fargate sizing is configured based on the topic. Each task runs a Kafka Delta Ingest container and a Datadog sidecar. So the way we run Kafka, we have read and write ACLs defined for all of our topics so that only specific applications can read or write. So we set additional Kafka properties in order to do that authorization. So on step 3, eventually Kafka Delta Ingest will write a Parquet file and a temporary Delta log entry to S3. Step 4, 4 and 5 are both implemented as part of the Delta RS commit. So first, step 4, we acquire a DynamoDB lock, and step 5, we do a rename of our temporary transaction log file to the actual specific version file name required to represent a valid Delta log transaction. Finally, with, yeah, actually, that was number 5. So outside of the primary data flow, we also have our nightly optimize and vacuum jobs running in Databricks, which also use our DynamoDB lock prior to running the optimize command. So some of the key aspects of the multi-writer design so that we can have multiple tasks handling the same Kafka topic. One, Delta RS includes a DynamoDB lock to fill in for missing S3 put if absent, which I mentioned, but I wanted to mention it one more time here so I could give you the link to QP's talk if you're interested. Highly recommend checking that out. He goes really deep on that. Another key aspect is that the partition offsets that represent the data accumulated from a specific Kafka partition are written into the Delta log. That way, you know, if a container goes down, another one comes back up and picks up that partition, it can read from the Delta log and see, okay, this is where we left off. I need to start from that offset. It'll do a seek and start consuming again. The last key aspect is as Kafka Delta Ingest is buffering data, if a consumer rebalance happens, we take a very simplistic approach and we just drop the buffer data, reseek to our initial offsets, and reconsume. All right, so now I'll describe what this looks like for us in production. So we have a multi-branch Jenkins pipeline that does a Docker image build that basically builds a Docker image of Kafka Delta Ingest, uploads it to our AWS ECR registry. We also have a Terraform pipeline, which includes a module that wraps all of our ECS config and our Kafka Delta Ingest parameters for each topic and generates a task definition for each service. And that definition comes from a config map for each topic. We provision Datadog monitors as well for lag and critical errors. And our task definition supplies our AWS secrets manager ARNs that are required for our Kafka topic authorization. Here's a little snippet of what our Terraform config looks like. I'm not going to go into detail since we're running out of time here, but you know, it's a pretty simple way to configure configure a Kafka Delta Ingest service to implement one of these streams. Then, of course, we have Datadog dashboards that we can filter by environment and table, and see all of the wonderful metrics that we emit to our Datadog sidecar. So just a few short words about what we have in mind for the future. We have a few ongoing challenges that are kind of top priority. One, our auto scalability needs improvement. Kafka rebalance makes this hard. I currently have a branch I'm working on to try to improve our rebalance handling to make auto scaling more effective. There are some memory improvements we need to make in Delta RS because we're storing the transaction log in a row-based format right now, and we need to store that in a column-based format to reduce some memory pressure issues. You know, the other two bullets I'm going to skip. And then some general enhancements beyond, these aren't causing issues for us at this time, but some things we'd like to see happen for Kafka Delta Ingest in the future is additional cloud support, trigger once semantics, because for these low volume topics, I'd love to do that thing you can do in Spark where you can do like a trigger once a day type thing and just read it everything for up to the current offset in Kafka and write that. And then finally, additional data formats, since we only handle JSON so far. So we love the value we're getting from Rust at Scribd. We've got other stuff written in Rust as well. We have a syslog endpoint that produces to Kafka. I've seen a couple of awesome Rust topics at the summit this week, one of which is about data fusion, which I recommend you checking out. The other is QP's talk, where he was talking about state right for formal verification of distributed problems. And that's it. We're ready for Q&A. As soon as I give some thanks, Misha was one of the primary contributors on Kafka Delta Ingest. Tyler and QP really helped get Delta RS and Kafka Delta Ingest kicked off. Neville and Florian were two other folks who were early contributors. And also, I'd like to extend an invite to anyone interested to come work with us at Scribd. It's a great place to work. Like I said, I've been there for a while, and I love it. So that's it. And I think we're ready for a Q&A.
Yeah, all right, everyone, let's thank Christian for his wonderful presentation. Questions, just raise your hand. I'll come by with the microphone. I saw a hand go up in the back first, and then I'll come up here. We only have a couple minutes left before lunch, so maybe just these 3 questions, and then people can talk to the speaker in the hall.
Check. Well, thanks for the talk. It was interesting to hear. You mentioned Datadog a couple of times. So can you go into that topic more? Like, what do you specifically choose to log into Datadog, and what's the reason behind this decision? Thanks.
I heard you. Could you clarify a part of that? I heard you say Datadog, but I didn't hear the specific.
Oh yeah. I was saying that you mentioned Datadog a couple of times. So what do you did you choose to log specifically into Datadog, and why? What was the reason behind this decision?
Yeah, so we've got a kind of a laundry list of counters that we log. So we log every time we deserialize a message, every time we transform a message. Not all messages get transformed, and if a failure happens, we also log the transform failed. We log we periodically log the number of arrow record batches that we have stored in memory. When we complete a write, we log the size of the Parquet data file that we wrote. Those are the big ones that I can think of off the top of my head. We periodically log the current lag that we have from Kafka. So we'll peek at the current offset. We'll look at the last offset we have buffered, and we'll submit a metric for that to Datadog as well, so that we can use that for Datadog monitors and alert if our lag gets too high.
Well, that's all the time we actually have today. Again, thanks to Christian for giving this wonderful presentation today. And you can probably find him out in the hall for additional questions. Otherwise, it's time for lunch. Enjoy.